Right, welcome to the Physics Tips for Cambridge Students YouTube channel. We are going to be looking at revision of paper 5, that is the second question on it. If you haven't watched the first video that is on question number 1, please go ahead and do so that you understand how to answer question number 1. Now, this video concerns question number 2. Okay, without much further ado, let's get started. Now, I'm going to start off with the tips on how to answer question number 2. Okay, so the first one is to read the question carefully and understand. Okay, so you read the question carefully and understand. So I recommend that you read it twice and then you understand. Okay, then you need to linearize the function that you are given. Okay, so you'll be given a function or an equation that governs everything that's going to be on the analysis in question number 2. And then please analyze that function. So I'm going to give an example. That is the February-March 2019 paper so that you can understand what I'm talking about. Okay, so let's move on to that. Right. So in this question, they're saying that a student is investigating the motion of a small steel ball in cooking oil. A measure of the oil's resistance to the ball's motion is called viscosity. Viscosity has the units of Pascal second. Okay. Then the student drops a ball into a cylinder of oil as shown in figure 2.1. The velocity of the ball is measured when it becomes constant, and then viscosity of the oil is determined. The experiment is repeated for different temperatures of oil. It is suggested that the viscosity, that symbol there, and the Celsius temperature theta are related by the equation that viscosity is equal to P theta to the power of Q, where P and Q are constants. So that is the function that I was talking about that you need to know how to linearize. So viscosity is equal to P theta to the power of Q. Okay, P theta to the power of Q. So going back to our writing. So there we are. So we have P theta to the power of Q. Okay, so viscosity is equal to that. Now, linearization of that function. You first of all, you take logarithms both sides. Okay, you've got to take logarithms both sides. Right. So let's see. So I suggest that you take, if you're not told, you just take logarithms to base 10 logs, not ln. So in this case, later on, I think you see that what they're referring to is logarithm to base 10. So log of viscosity should equal to log of P, right, plus log of theta to the power of Q. You should be able to identify that. So log, I'll just say LG, that is equal to log P plus Q log, let's just say LG theta. Okay, so that is that. Now rearranging it so that it is in the form y is equal to mx plus c, you have log of nu is equal to q log theta plus log p. Okay, so there we are. So in the form of y is equal to mx plus c. So there we are. So log of y of nu, that is our viscosity, should equal the y. So that's what's going to go on our y-axis, and then this one will go on our x-axis. So which means our gradient there is going to be q, and then the y-intercept is going to be equal to log p. So it's not enough to leave it like this, because you find that when they ask you the question, you have to leave it where it is supposed to be. Okay, so it says where p and q are constants. Right, so All right. So that's going to be this one. Check out this one. Yes, so it says a graph is plotted of um, so a graph is plotted of log viscosity on the y-axis against log of theta on the x-axis. Determine the expression for the gradient in the y-intercept. So the expressions for the gradient and y-intercept are the ones that we found there, q and log p. Okay, so q and log p are the values that we found there. So q is our gradient, which is m on y is equal to mx plus c. Log p is our y-intercept in that regard. Okay. And then you get 1 mark if you do that. Right. Going forward, you are then required to fill out a table. Okay, so you'll be required to fill out a table and you'll be given that. So it says values of theta and nu are given in figure 2.2. That is the viscosity. So we have that given there. So we have that one given with uncertainty, that the viscosity is given with the associated uncertainty, right? And you then find the logarithm of that. So you just work out logarithm to base 10 of that, okay, of theta, and the logarithm to base 10 of log of that is of viscosity. Please bear in mind that the table, that is the heading of the table, is telling you that it's times 10 to the power of minus 3 of a Pascal. So which means your answer must be times 10 to the power of minus 3 of a Pascal. Then they're going to ask you to calculate the uncertainty. Okay, so I'm going to give you an example where you have theta being equal to 38. So I'll work out that one and then we can see how it goes. Okay, so right, so we have theta equal to 38. So log, if on a calculator, if you say log of 38, that is to base 10 there, let's work it out, you should get 1.58 there. Now, one thing I need to emphasize here, you find we are going to treat these as 2SF. Okay, we're going to treat these as 2SF. So when you are taking logarithms, then these SF change to decimal places. So you have got to state to two decimal places there. Okay, so SF change to decimal places when you take logarithms. Okay, SF change to decimal places when you're taking logarithms. I hope that makes sense. Forgive the untidiness there. Okay, so we are allowed, however, to add one more decimal place. You're allowed to add one more decimal place if you want. So it can be 1.580. Okay, that is that. Moving on. Should be this one. Yes, so the first one there, we've got the value for it, which we said theta was 38, and then viscosity was 41. So viscosity was 41, so which means you can also find the logarithm of 41. Now, when you find the logarithm of 41 there, it should come to be 1.61. Okay, it should be 1.61. That is for the viscosity part. So for the viscosity part, let's see. Let's start on a fresh page. Right. Okay. So we have log of 41 should equal 1.61. Again, these are 2 SF, so SF should change to decimal places when you're taking logarithms. Very, very important. You don't just express your answer anyhow. So it has to be that, or you can add one more. Okay, add one more. One more decimal place can be added. Now, we then come up to finding the error bars for this value, right? Getting error bars for this value. Now, there are 3 instances there. I think you should pay particular attention to the 3. The first one is, so we're going to take our 41, say 1.61 is our log so this is a log of viscosity. Okay, so these are the ones that have error bars. So you're going to take the 1.61 is our middle value. We're going to have a higher value there, and then we're going to have a lower value. Okay, so right, we have 41 there. Let me go back to the question and then show you how I am taking this. We have 41 plus or minus 1. Okay, 41 plus or minus 1. So which means our value of viscosity is between 40, right? So we have got the value. Let's just start off with the viscosity value. So if the viscosity value is 42 and then 40. So it's somewhere in between. So we've got the 41 there, then plus 1, you go to 42, minus 1, you get to 40. Okay, so if you say log of 41 minus log of 40, okay, that becomes uncertainty, but on the lower case. Okay, you're saying the mid one minus the lower one. Okay, then here you have that. Then you've got the higher value. You're now saying log of 42 minus log of 41. So this also is the uncertainty. Okay, so this is the uncertainty in this value. Okay, the uncertainty in the 1.61. That's what we're trying to find. Don't confuse it for a value. So this is uncertainty for the first value for when viscosity is equal to 41. Remember, we got 1.61. So we want to find the uncertainty of that 1.61. So we can go highest value minus middle value. Okay, so highest minus middle, or you can go middle minus lowest. Okay, we still get the uncertainty there. Okay, or you can go highest minus lowest divided by 2. That's the range. Okay, so half the range. So it's going to be log of 42 minus log of 40, or divided by 2. So we get the uncertainty if we do it that way again. So there are 3 cases, like I said earlier on. We have highest minus middle one, right? Which is so that's log of 42 minus log of 41. And then we have got middle minus lowest, that is log of 41 minus log of 40. Or you can go log of 42 minus log of 40 divided by 2. Now, I urge you to be very, very consistent. Okay, you should be consistent. If you choose to use, highest minus the middle one, please stick to that throughout your readings. Okay, stick to that throughout your readings. So highest minus middle one, or medium minus lowest, or highest minus lowest divided by 2. Okay, so let me get to where I was writing. So there we are. So we have this value there, where you have got this log of 42 minus log of 41, or you go log of 41 minus log of 40, or you can go log of 42 minus log of 40 divided by 2. So that is that half the range. Okay, so these are the three possible. So if you have chosen to go this minus that, please stick to that throughout. If you have chosen to go this minus that, please go you stick to that throughout, or this minus that divided by 2, please. So remember, highest minus lowest is always divided by 2. Okay, now if you work that out, you find that you should get 0.01. Okay, you should get 0.01 if you work that out. So 0.01. Now, in this particular question, remember, absolute uncertainties are stated to correct to 1 SF all the time. That's what I always recommend. But in this paper, they don't mind if you use 2 SF there. We can 0, or you can use as 1, no problem. But I always urge my students to use 1 SF. Just stick to the 1 SF that I've taught you. But I'm saying they don't penalize you for using 2 SF in there. Okay. So now this is going to be the error bar that you're going to plot. Okay. So we are going to plot the graph. Remember, let's go back and see what we're plotting against. Right, so we have log viscosity on the y-axis versus log theta on the x-axis, q and log p. So log p is our intercept. Okay, let's go back. Right. Right, so there we are. So it's going to be like this. So this one is going to be your log viscosity, and then this is going to be your log theta, and then the y-intercept, that is, now it depends on the question paper. If they didn't start from 0, then this is not the y-intercept. Okay, please, that's a false origin mark if you do that. And please, since your log theta values, remember you have used the log theta values times 10 to the power of minus 3. It's very important to not ignore the power of 10 error. The power of 10 error is very, very important. So, in other words, when they say power of 10, that's when someone ignores or forgets that everything is being multiplied times 10 to the power of minus 3. So in the calculations, you then get everything wrong. So please make sure that you master that. So if this is starting from 0, then automatically this is going to be a log p. Okay. And, well, normally in this paper, they already give you figures. Okay, so the scale that you're going to use is already determined. So it's going to be easy for you to plot the graph. Now, the only thing now they're going to say line of best fit. So your line of best fit, you should have a balance of points at the top and as well as at the bottom. Clearly, one of the points can be an outlier. Okay, you must circle it and show that that's an anomalous point, and you won't use it in the determining of the line of best fit. Okay, so there must be a balance of points up and down. Okay, as you can see, I've chosen that to be an anomalous point, so it won't be considered in finding my line of best fit. Now, going back to the plotting of the error bars, now we found that this one was 0.01. So you go, so these are on log theta. Is it? Let's see. No, they're supposed to be on viscosity. Which one is it? Yes. So the error bars are on viscosity. So the vertical error bars. So which means you plot 0.01 going up and 0.01 going down. Okay, right on the point. So 0.01 going up, 0.01 going down. I just did for 1. Well, the second point comes in, and then you find the error bar. It could be 0.01 again. This one 0.02, this one 0.02, and then the last one 0.03. Okay, so equal points are 0.03 going up, 0.03 going down. So that's how it's going to be. And then you have your error bars plotted correctly like that. Now, you then are supposed to draw the line of worst fit. Now, the line of worst fit must, in essence, go past every point, okay, every point or every error bar, okay. So normally it is from the top of the top error bar to the bottom of the bottom error bar, okay. So it crosses the line of best fit normally. But if you find that one of the error bars is being left out in the process, make sure you incorporate it by making sure that the line of worst fit passes through all the error bars that you've plotted. I hope that makes sense. Now, this line of worst fit can be a broken line. Okay, you can make it a broken line, or you can label it, okay, line of worst fit. Okay, line of worst fit. That is, you've got to write in full, line of worst fit. And then this one, you have said line of best fit. Okay, so in full again. So it's very, very important to do that. Sometimes they say worst acceptable line, something like that. So okay. So I think that is it in terms of drawing error bars and plotting the graph. Then, well, they always give you they always look at the line of best fit, whether it passes through a certain coordinate here at the bottom, certain coordinate at the top. So please make sure there's a balance of points. Otherwise, they deduct a mark for the line of best fit. Very, very important. Now, you ought to have a triangle. Okay, a triangle must be drawn. Triangle must cover that point. So the triangle must cover at least 50% of the graph drawn. That is for the line of best fit, and then you have another triangle for the line of worst fit to show the coordinates that you are using for the calculation of the gradient. Make sure that the points that you choose are on the line of best fit. They must always be on the line of best fit or on the line of worst fit. Don't choose a point which does not lie, like this point. It does not lie on the line of best fit, so must not be chosen. So choose a point that is there and which you can easily read as well, so that you get an accurate value of the gradient. Now, the formulas that you're supposed to apply, the error in the gradient, you find it by saying the gradient of worst fit line, let's just say wow, minus gradient of the line of best fit. Okay, so whichever one is the greater subtracts the other. So the error in the gradient, that's the uncertainty in the gradient that you find. Also, the uncertainty in the y-intercept is the same thing. Uncertainty in the line of best fit minus the uncertainty in the line of worst fit. Whichever is greater, the modulus of it is what you take. Then you are going to use these in the calculations, in the questions that come below. But most importantly, please do not forget that there is a power of 10 that is associated in the values, because you kind of drop these when you start showing the table. Okay, so on the table, you find that this when you record the table, the numbers are now whole numbers. In other words, they're not decimals. But then when you do the calculations, do not drop the 10 to the power of minus 3 that is supposed to be there. Okay, now to sum up, so that I don't make this video too long, I think I need to go over the points that I've written there. I think I've gone over pretty much all of them. So I said, read the question carefully and understand before you start answering. Linearize the function. I've shown you how to linearize these logarithmic functions so that you get the gradient and the intercept. Then beware of the power of 10 error. I've emphasized that one. Beware of the power of 10 error. And then refer to the gradient and the y-intercept in all the calculations. Okay. refer to the gradient and intercept in all the calculations. Now in this, what I mean is whether they want you to find the constants. Remember, in some stage, we said that the gradient is p, and q log p log q. Sorry, log p is the intercept, and q is the gradient, right? So they may want you to find p with its associated uncertainty. So p will be equal to 10 to the power of intercept, right? Because you know that log p is equal to the y-intercept, so which means p will be equal to 10 to the power of the y-intercept. Now to get that, remember, we are now saying the intercept of west fit line. So 10 to the power of the intercept of west fit line, right, minus 10 to the power of the intercept of best fit line. Okay, so that becomes the error in P. I hope that makes sense. Okay, again, for finding Q, that is the error in the gradient. So we say that Q is the gradient. So the gradient of west fit line minus gradient of best fit line. And that you have answered all the questions. Okay, I think if you have any questions, please let me know in the comment section, and please make sure you like, you comment, you share this video to as many students as you can, and please push the notification bell again to get more notifications on videos that I'm going to make in the future. Okay, signing out.